No. Okay, thank you for that introduction. It's not a Feigin-Frenkel conjecture, it's a Feigin-Frenkel center. It's definitely a different object. So I don't know a lot of things about the conjecture. Center is in a way much easier. And anyway, whatever I'm going to tell you today is much easier than the Feigin-Frenkel conjecture. Right, so I will introduce some notation. G is a complex, small g is a complex Lie algebra. The big G is a reductive complex Lie group. So Lie algebra is finite dimensional. I want my group to be connected. The ground field is complex numbers, so everything in characteristic 0. When we have the symmetric algebra of G, of Lie algebra G, we have the enveloping algebra, U of G of Lie algebra G. It has a center, and the symmetric algebra has a subring, a subalgebra of symmetric invariants. So the invariance of the Lie algebra G in the symmetric algebra, it's the same as the invariance of a group G in the polynomial ring of functions on the coadjoint, on the dual space of G, so the invariance of a coadjoint action. And this object as an algebra is isomorphic to the center of the enveloping algebra because we are in characteristic 0, and the Lie algebra is finite dimensional. So for this isomorphism, you need two ingredients. The first one is characteristic 0. The second one is that your Lie algebra is finite dimensional. Reductive or not is actually not important. It works for any algebra. Reductive case has some other nice features. So for example, this ring of symmetric invariance is a polynomial ring because there is a Cartan subalgebra T in G and the while group. The normalizer of a Cartan subalgebra vector by the centralizer, which is a finite reflection group if you consider its action on the torus, and by the Chevalier restriction theorem, the symmetric invariants of G are isomorphic to the regular invariants of while group. So you have here a polynomial ring in L generators. The L is the dimension of the Cartan, and which is also known as the rank of the group of the algebra G. So these are really very well-known objects and even symbols. Another standard thing which occurs in the title of my talk is the symmetrization map. So you can define it for any vector space. It's a map from a symmetric algebra to the tensor algebra. So you take something symmetric and symmetrize it in order to get an element in the tensor algebra where your factors don't commute any longer. And the usual thing is to vector to take a quotient of this map from the tensor algebra of some Lie algebra Q to the enveloping algebra. So first you go from the symmetric algebra to the tensor algebra, and from the tensor algebra you can go to the enveloping algebra of Lie algebra Q. And this map is usually known as the symmetrization map for Lie algebras. It is a homomorphism of Q models. It's not a homomorphism of algebras. So this is one of the drawbacks of this construction. So symmetrization does not respect multiplication, but it respects the action of Q, a group, or Lie algebra, whichever you want. So we have an isomorphism of vector spaces between the symmetric invariants and the center of the enveloping algebra of Q. And again, Q can be finite dimensional or infinite dimensional. It doesn't matter at this stage. Right, I have introduced notation for reductive Lie algebras. The object on this slide is not any longer reductive. This is a so-called Takeev Lie algebra, generalized Takeev algebra, or truncated current algebra. We multiply our algebra G with polynomials in T and then take the quotient by T to the power of n. So this is again a finite dimensional Lie algebra. It's no longer reductive because T to the n is equal to 0. If n is greater than 1, then you have here the nilpotent radical, which consists of n minus 1 copies of G. But still, you can define the symmetric invariance for any Lie algebra. It doesn't matter whether it's reductive or not. And maybe by a strange coincidence, in case of a generalized Takif Lie algebra, the ring of symmetric invariance is still a polynomial ring, and the number of its generators is easy to get. It's n multiplied by the rank of G. So we have n copies of G, and then you also need, so to say, n copies of each basic invariant, basic symmetric invariance of G, in order to get the generators for the generalized Takif algebra, or for the current algebra. So this was proven by Rais and Tawel, and almost at the same time by Feigin and Frenkel in a different context, in the context of enveloping algebras and not on a symmetric level. Right, so symmetric invariance related to the co-adjoint action, they are actually invariance of Lie algebra of a group for the co-adjoint action. And here, so I consider I write first as a vector space, the dual space of my current algebra, truncated current algebra, generalized Takif algebra, so the dual space of a copy of G, and multiplying G with the image of T and take the dual, and so on. It's finite, you need just n copies. And now how does Lie algebra act here? It's, so to say, it shifts everything to the right. Now, you have to multiply with the positive powers of T, so as a G model, every copy is stable. So every copy of G here is stable under the action of G. But if you consider the action of G multiplied with the image of T, then you have to move your components one step to the right. Because here you're multiplying one with T bar, you multiply T bar again with T bar, and you get T bar squared, and so on. So the action, the dual co-adjoint action of Lie algebra in this picture goes to the right. And if you apply anything with a positive power of T to the last summand, we're just going to get 0. And in the same way, the quotient of the loop algebra in this case acts on the sum of copies of a dual space of G multiplied with negative powers of T. No, so instead of image of T to the power n minus 1, I'm just taking T to the power minus 1, the inverse of T. It's not a question. And the action is still to the right, and this I'm considering as a quotient of a loop algebra by the positive part. So which means again that if you act with something having a positive power of T on this last summand here, on the most right summand, then the result is 0. Right? So here, this is an honest dual space of something finite dimensional. And here, this is also finite dimensional, but we consider it as a subspace of something infinite dimensional. And with something infinite dimensional is a quotient of loop algebra by its positive part, and then we're also taking the dual. Right, why do I want to consider all these things? Because the first one is just finite dimensional and it exists for any given n. But if you look on it with negative powers of T, then of course you can go on here to the left, T to the power minus n, and then comes T to the power minus n minus 1, and so on. So in a certain way, this second direct sum is infinite on the left end. So we can continue here. So we can take a direct element of these spaces, Wn.
Can I ask a small question?
Oh, yeah, certainly.
So first of all, I wanted to apologize for jumping in late. I mean, I completely missed it today. was an unusual time for the seminar, so my apologies. I also wanted to ask, you said that this truncated current algebra is a generalized Takif algebra. I'm not familiar with the concept of Takif algebra, but clearly, if this is being given an actual name, it means it's supposed to encompass or to capture some feature of it. So what makes it a Takif algebra as opposed to just a truncated current algebra?
Oh, no, Takif is a family name. So it's a mathematician who first considered these algebras in case n is equal to 2, and he proved that the symmetric algebra is a polynomial ring, but just in case of n equals to 2.
Ah, I see. Okay.
So it's a name of a mathematician.
Yeah, no, I figured it was, but yeah, okay.
So he had some results. I think he also had some results on the representation theory of his algebras. In case n is equal to 2, and the name is relatively widely used nowadays in mathematics.
Thank you.
All right, thanks. Yeah, that was an easy question. Right, so now I'm taking direct limits of what can be thought of as a dual space of a generalized Takif algebra. And I'm also taking the direct limit of invariance, symmetric invariance. And this direct limit is a polynomial ring, but now in infinitely many variables. So because at each stage it's a polynomial ring, and you have embeddings, you have also embeddings for the invariance because of this action, which shifts everything to the right. So this object is this direct limit. You can also describe it like that. The invariance of a positive part of a loop algebra in the negative part. But you have to think about this symmetric algebra of a negative part of a loop algebra really as a quotient. So whenever you get a positive power of t or a constant, then this term is 0. So S of g hat minus is actually a quotient of a loop algebra by its positive part, and then I'm taking the invariance of a positive part in it, and it's a direct limit of something which comes from a truncated current algebras. Right. So this object, which is now I have denoted as z bar of g hat. It's again the definition, the invariance of a positive part in the quotient by a positive part. This object has two features. So first of all, it is a polynomial ring, and its algebraically independent generators can be described very explicitly. And this was done by Raiz and Tovel. They were generalizing results of Takif, actually. So they read his works and they started to think about it and generalized it for any n. So they obtained the same results for any n not equal to 2 necessary. And another feature of this thing is that there is a quantization in a certain sense. No, sorry, it comes later. So the first feature is that this algebra is Poisson commutative. I will explain on the next slide what I mean by the Poisson bracket and by being Poisson commutative. But if you know, it just means that the Poisson bracket vanishes on this subalgebra, and the Poisson algebra is defined on a symmetric algebra of any Lie algebra. There are many ways to do it. All right, so if you don't know about the definition of a Poisson bracket here, we have three different ways to do it. So on symmetric algebra of any Lie algebra, finite or infinite dimensional, it doesn't matter. You can define a so-called Poisson bracket. So for elements of degree 1, for elements from the Lie algebra, this is just the commutator. And then one has to extend this bracket by the Leibniz rule. Or you can do it directly. We take two polynomials, take an element from the dual space, differentials at it was element gamma. You take the commutator and the Lie algebra and then evaluate your function, linear function gamma at the commutator. And this is the Poisson bracket, which is a function, polynomial function. This is the value of our polynomial function at the point gamma. And the third way uses enveloping algebra and the fact that the symmetric algebra is the associated gradient of the enveloping. So in the enveloping, we're taking the commutators of two elements, and this corresponds to the Poisson bracket of the classes in the symmetric algebra.
Can I ask a question about the previous slide?
Yes, there's much information.
So when you say that algebra is Poisson commutative, is it actually in the Poisson center of the big algebra, or it's that's not true?
Of The Poisson center of a big algebra, I suppose, is 0.
It's not in the center of the big Poisson. Okay.
Because just for this algebra, the center doesn't exist.
Okay.
It is constant. As for the center, you have to complete.
Okay.
I'd say just a few words about it a bit later.
Can I also ask, just in type A, does this algebra, can you present it explicitly, you know, if, so the usual symmetric invariance is just symmetric polynomials, but what is this extension of it?
You just have to polarize them. Actually, the whole talk is about explicit formulas. So you will see a lot of explicit formulas later on. For the symmetric invariance, it's relatively easy. You just polarize them. And it doesn't depend on type. It's type free.
Okay.
So like you write, instead of x, you write x1 plus sx2, and you just look for homogeneous parts in S. So this is our easiest example of polarization, something.
Okay, thanks.
And this is how you obtained invariance for generalized Tekif algebras. All right, so I have defined a Poisson bracket in 3 possible ways, and the third definition uses associated graded of enveloping algebra. So in these terms, yes, with symmetric invariance, they are the Poisson center of S of Q, but this doesn't have to exist always. Constants are there, but maybe nothing else. Okay, so subalgebra is Poisson commutative if a Poisson bracket vanishes on it. That is the usual definition. And if you have something Poisson commutative in the symmetric algebra, then the quantization problem arises. What does it mean? You are looking for something really commutative in the enveloping algebra. And quantization in the sense that enveloping algebra is already quantum enough. I know that many people would not agree with this statement. There's no additional Q here. So quantum for this talk is just the enveloping algebra. In comparison to the classical part, which is given by the symmetric algebra with a Poisson bracket, with the classical part, with the quantum part. And you are looking for something honestly commutative in the enveloping algebra, such that the subalgebra generated by the symbols of our elements coincides with A. So A existed before, and you want to quantize it, or I want to quantize it. All right, so what is one of possible definitions of a Feigin-Frenkel center? This is a unique quantization of the algebra Z bar of G hat. So we have defined that subalgebra of invariance, very quite easy definition. And the Feigin-Frenkel center is something sitting in the enveloping algebra, also of a negative part of a loop algebra. It sits inside the G invariance, the algebra Gx. And this subalgebra is the unique quantization of Z bar of G hat. The associated graded coincides with it. It's a commutative subalgebra. It's a polynomial ring in infinitely many variables, generators. So the first proof of this result is given by Boris Feigin and Feigin-Frenkel in 1992. And very roughly speaking, what we are doing, we're still taking the invariance of a positive part in the enveloping algebra of a negative part. But you have to consider it as a quotient, and not just a quotient of a loop algebra, but you have go to the Kac-Moody algebra a little bit cut. So I'm just taking one-dimensional central extension, but still you have to do it and take the quotient at a critical level when this definition works. So what is the critical level? All right, so we need the dual Coxeter number. We need the right normalization of a commutator in the Kac-Moody algebra. And then we can define the critical level as big K plus H check. And the reason why this thing works, why this algebra of invariance is actually commutative. So there's no reason why it should be. maybe the reason is that this quotient is a vertex algebra. So it has a certain additional structure. And when, so to say, its center in the vertex sense is a commutative algebra. So just by taking invariance, such invariance doesn't guarantee you that you are getting something commutative. So in order to prove it, you really need vertex algebras. All right, but this is kind of, this is already have been for a long time on the market. So it has been used for a lot other problems. So some other features of a Feigin-Frenkel center. It's isomorphic as an algebra to the center of a completed enveloping algebra. So just answering question of million. The center of G hat is trivial. I just have elements from the field of complex numbers. So you have to complete this thing on the critical level, and then there is a center, and the Feigin-Frenkel center is kind of, if you take it here in the negative part, so it's not even a quotient, it's isomorphic to it. But you are forgetting, so to say, all the positive powers of T, and consider here only the negative powers of T. So all positive powers of T disappear. So basically we are dealing here with finite sums. Another feature that you have something commutative, something really large and commutative in the enveloping algebra of G hat minus. Then for any two-sided ideal, we can consider a quotient of this algebra in order to obtain some other algebra, and the quotient of a Feigin-Frenkel center will be a commutative subalgebra of that quotient. So in this way, two rather classical quantization problems are solved. So the first problem is related to the Godin model, and it was done by Feigin-Frenkel and Resetichhin, so also about 30 years ago. And another application is to the so-called Mishenko-Fomenko subalgebras. So I'm not going to tell you anything about Godin model, but I will tell you a few things about Mishenko-Fomenko subalgebras and how this problem is solved with the help of Feigin-Frenkel center. Okay, so what are first quantum Mishenko-Fomenko subalgebras? I know, first are classical. All right, so first I define the classical one, and then I tell you what is the quantum. So G here is reductive Lie algebra, but it can be any Lie algebra. We are taking symmetric invariance of G, and I'm fixing some element in the dual space and taking iterated partial derivatives in the direction of gamma of all symmetric invariance. It actually suffices just to take the generators, and whatever you obtained, the smallest subalgebra generated by these things is called the Mishenko-Fomenko subalgebra. It is Poisson commutative, as Mishenko and Fomenko showed. They were the first to consider such things. And then Winberg formulated the quantization problem for this subalgebras, so the standard quantization problem. He wanted to find something commutative in the U of G, such that the associated gradient of F is Mishenko-Fomenko associated with gamma. So there are several solutions, and some of them are using Yangians, some of them are using Symmetrization Map. And the first general solution, which is type-free and works for all reductive Lie algebras, was presented by Leonid Rybnikov in 2006, and he has used the Feigin-Frenkel center, as we agreed, it's algebra of G hat minus, and a certain map from it to the U of G, so you take in a quotient. So we're sending x times t to the power of r to x times z to the power of r plus gamma of x if r is equal to -1. So this is kind of a quantum shift, and you forget all your g's. So I go just to the elements of the field of complex numbers. His results are the image is independent of the choice of your complex number z. The image is, of course, commutative because you have studies with something commutative. And this image is large, so it's large enough to contain the Mishenko-Fomenko subalgebra. And in case gamma is regular semi-simple, then actually the associated gradient of F gamma coincides with Mishenko-Fomenko. So it solves Winberg's quantization problem for reductive Lie algebras, and in case of regular semi-simple gamma, within a certain probability.
Just a quick question. What about, say, a regular nilpotent element, or just an arbitrary regular element, not necessarily?
Yeah, it comes in, I don't know, 30 seconds.
Oh, okay.
Can I make also a comment, which is that this problem was solved by Rybnikov, but independently was also solved by Feigin-Frenkel and myself same year.
I know, I'm going to mention it. But you were, 4 years later?
Were we? I think we did it in 2006, actually, but.
I wonder if I have the title, the date. I certainly mentioned your paper. All right. Okay, so you think you did it, of course you did it independently, no problem about that, but I thought it was a bit later. Right. But returning to Peter's question, what about regular elements? So first, I want to remind you about the inclusion. The inclusion was proven by Rybnikov, well, of course, it also proven by Valerio and Feigin-Frenkel for all gammas, independently regular singular, and but also by a result of Tarasov. This is what Rybnikov has used. If gamma is a maximal Poisson commutative subalgebra of S of G, if gamma is regular semi-simple, and you see if you have something which is already maximal Poisson commutative and you have this inclusion, then the second one cannot be larger than the first one. So that's kind of guarantees you the equality. And actually, this is also true for any regular element. For any regular element, this subalgebra is maximal. So the Mishenko-Fomenko associated with any regular element is maximal, and this I have shown together with Panishov in 2008. And when the paper was published in 2010, I suppose you have finished it a bit earlier. And independently, Feigin-Frenkel and Valerio Toledano-Loredo have proven that for any regular gamma, if gamma bar coincide with the associated gradient of F gamma, so the quantization problem is solved. Suddenly, they had an absolutely different proof, and they have also shown this inclusion by their methods, and they have formulated the following conjecture that the image, the graded image of a quantum Feigin-Frenkel, Mishenko-Fomenko, quantum Mishenko-Fomenko subalgebra always coincides with the usual Mishenko-Fomenko subalgebra. So also for singular gammas. So for regular, this is settled, so in many different ways by now. For singular, it's not exactly settled, so it's true in types A and C. So in type A, first it was done by Molev and Futorny, and then we obtained a new proof for type A, which is also applicable in type C. So for SLN and SP2N, the problem is solved. It's the conjecture of Feigin-Frenkel and Toledano-Loredo is settled for types A and C. But for example, it's open for the orthogonal Lie algebra. So if you are interested, well, the field is open. There are many non-regular elements in the orthogonal algebra. Okay, so now a few more things about this big center, the Feigin-Frenkel center. It's possible to a certain extent to describe its structure. So first I will introduce this rather standard notation. So G and A in the square brackets, this is just G multiplied by T to the power of A, and the same for the elements of the Lie algebra. When we consider the partial derivatives, with respect to T of elements of a Feigin-Frenkel center or whatever of enveloping algebra. So the Feigin-Frenkel center is a polynomial ring with infinitely many generators. And there is a distinguished generators. A complete set of them is called a complete set of Sigal-Sugawara vectors. We should have L of them. L is the rank of G. And all the other generators, they are partial derivatives, iterated partial derivatives of these distinguished ones with respect to G. Okay, so you have L generators that are really important, and you obtain all the others by applying this operator. You can also describe the symbols of this distinguished generator Sigal-Sugawara vectors. If we evaluate at t equal to 1, then you get an isomorphism between symmetric algebra of G minus 1 and G. And in this notation, the elements of this element is 1 to SL. They are obtained as symmetrizations of H minus 1. The H is actually a symmetric invariant of G. So this is something reductive finite dimensional and very standard. So you take a symmetric invariant of G, which are very well known, and you shift it, so to say, to the -1 degree. So replace all elements from the Lie algebra by the same elements multiplied to the inverse of T, symmetrize. And then also there are some other summands, and these summands are rather mysterious. So in the usual filtration of enveloping algebra, they belong to the summands of degree smaller than D. The degree in T is still minus D. This can be arranged in this way, but the explicit formulas for them really have been a mystery for quite a long time. So I'll come into the explicit formulas, I think, on the next slide, but before we do so, I want to mention another result of Rybnikov. This is another structural description of a Feigin-Frenkel center. So you just need one element, the quadratic Casimir element, shifted to the degree -1. So you see what the usual Casimir element, just the sum of xi squared. Xi is an orthonormal basis of G with respect to some non-degenerate scalar product. And then you just shift all your variables to the degree -1, and the polynomial don't do anything to the polynomial. So the result is that the Feigin-Frenkel center is the centralizer of this single element. So you don't really, if you don't want to, you don't have to know anything about completed enveloping algebras, and you want to check whether your element lies in the Feigin-Frenkel center. Just compute its commutator with the quadratic Casimir to the degree -1. All right, so now we're ready to the subject of this talk, explicit formulas, and first in type A. So they appeared in 2006 and then in 2009 for the first time, and that time only for type A. So first we begin with the symmetric invariance of G11, where coefficients of a characteristic polynomial. Okay, it's not bad as yet. Also, I want tau to stand for the minus partial derivative with respect to t. And I need the following convention. If you take the commutator with tau of something x with degree a, then you get minus a, and x changes its degree to a -1. And another convention is that if you apply tau to 1 or to any other complex number, you get 0. So for example, this would lead to the following. If I have tau multiplied by x -1, and I apply it to 1, multiply it with 1, when we take here the commutator brings x in degree -2, plus the product in the other direction, but the product in the other direction is 0 because tau applied to 1 is 0. Okay, so these are conventions, and then you have to build a matrix, an n times n matrix. Some elements belong to the Lie algebra. So you take the matrix units, shift them to the degree -1, and then you also add the identity matrix multiplied by this operator tau. And you compute the column determinant of this matrix. And because this matrix has a certain special property, it's so-called Manin matrix, the symmetrized determinant will be the same. So I'll say a few words about these objects because I don't think everyone have seen them already. So this is the repetition of what we are doing, taking matrix units, shift them to a degree -1, and add with tau multiplied by the identity matrix. What is a Manin matrix? It makes sense only for non-commutative rings. Over fields, every matrix is Manin. Over non-commutative rings, it's, or non-commutative, what do you say it? Shift couple. It makes sense. So the commutator between Aij and AKL is the same as the commutator between AKJ and AIL. So you just switch here I and K in this formula. So for example, if I and K are equal, then this condition is void. All right, so here is an example for n equal to 2, what we are doing. So the anti-diagonal elements were elements from the loop algebra. And here you have an element from a loop algebra, but then also you add our differential operator, our partial differential operator. First, let us check a few things. Why is this matrix Manin? There are no conditions on the elements lying in the same line, in the same row, but the elements lying in the same column have to commute with each other. All right, so I've checked, they commute. The same for these two elements, they have to commute with each other, and they do. And then I take a commutator of diagonal elements, this one and this one. It has to coincide with the commutator of the anti-diagonal elements, but in this direction. First, this element, and then the commutator of this element, and you see they coincide. This is here in the yellow color. So I have checked whether this matrix is really Manin. There is a theory about Manin matrices. You can do linear algebra for them, and this is actually the largest class of matrices where you can do linear algebra. So usual things. Like, for example, computing determinants and having the multiplicativity property for your determinants. All right, by column determinant, yeah, because if you compute the row determinant, the result is not going to be the same and it doesn't bring the right formula. Column determinant means that you don't use the usual Leibniz formula, you use it slightly different. So you take always the product such that the first element is from the first column and the second element is from the second column, and here also in this sequence. Right, so this is the column determinant. Then we can multiply and write it as a sum. And what we are interested in is the coefficients in front of the powers of tau. So I write it as a polynomial in tau, and you see we have here two non-trivial coefficients, and the last coefficient is 1, which is of no interest. So the coefficients are elements of a Feigin-Frenkel center. They belong to those distinguished generators I have told you about. The column determinant, right? But I don't want the column determinant. I want the symmetrized determinant. And it means that you have to take the product in this sequence of factors, and then also add the product where you take this one first and this one second. But it's going to be the same because you change the sequence of factors for this product, for the diagonal product, and you change the sequence of factors for the anti-diagonal elements. And the first one comes with sign plus, the second comes with the sign minus, and they're equal. So for this matrix, the column determinant coincides with the symmetrized determinant. And the coefficients, if you take the column determinant, the coefficients of this polynomial are our Segal-Sugawara vectors, which we want to describe. Okay, so now instead of writing a column determinant, I'm writing the symmetrized determinant of the same matrix. Right? So this is the symmetrization map. So delta n is the determinant of the matrix, so this is symmetric invariance, basic symmetric invariant of GLN. What is non-trivial here, the symmetrization map is applied to the product of tau, so this partial derivative, with something from a symmetric algebra of Lie algebra. So if you symmetrize it, you have to symmetrize the partial derivative with the other elements. So it's like, it's going to stay on the first place, second place, and all other places. And the formula is continuous. You have always here tau to the power of k, and when the basic symmetric invariant, the product of minus of the size n minus k. Right? Now, I'm not quite happy with this formula. I want all my powers of tau to have the same parity. So I'm going to apply the while involution of GLN in order to get rid, so to say, of odd summands or even summands. Right, so theta, while involution, it multiplies delta k with minus 1 to the power of k. The quadratic Casimir is an eigenvector, so while involution acts on the Feigin-Frenkel center, and it can choose a set of complete set of Shigosugawara vectors that are eigenvectors of theta. So you just apply theta and add, or take the difference. So these are the new formulas, slightly modified formulas, explicit formulas for the elements of the Shigosugawara vectors, generators of Feigin-Frenkel center. So here's once again. The formula looks maybe a bit strange, but and if you look on Molev's formulas, they don't look any better. All of his formulas look rather bad. And well, we just with partial derivatives, now it's in the even powers of the symmetrization map, binomial coefficient, and well, the sum over R between I and K divided by 2. So this is not the original form, so the original authors of this construction didn't really bother about the symmetrization map. And another difference is that we have the degrees of the symmetric invariance that appear here. They all have one and the same parity. Now, rather rhetorical question, is there any reasonable connection between delta k and delta k minus 2? Yes, okay, there is a connection. You can apply the G invariant Laplacian, and again, from delta k, depends on your norm, how you normalize the operator delta k minus 2 multiplied by a certain rational number. But actually, this doesn't help us a bit.
So, okay. Sorry, can I?
Yep.
So each one of these, so if I were to think of the symmetric invariants as just being like symmetric polynomials, I mean, it's type A, these delta k's are like elementary symmetric functions? And
yeah, if you restrict it to the Cartan subspace, yes, it will be just the sum of products. No, elementary symmetric functions, if you restrict to the Cartan subspace, yes, you're going to get elementary symmetric functions.
I mean, so I should think of it as infinitely, what you're describing as infinitely many copies of the ring of symmetric functions. No? Or?
No, I have.
I'm just trying to interpret. So this is a sum of.
This is a finite sum, first of all. So this is definitely finite.
So the first term here is somehow weighted by t to the -1, and the remaining terms are weighted by t to the negative odd numbers. I'm just trying to interpret.
No, all powers of t are -1.
All powers of t are -1, but then you have these taus that are also.
Yeah. If you apply it afterwards, yeah. So first you just take all powers of t as -1, and then you apply this partial derivative, and it's going to so to say decrease the power of t. Definitely.
So do I understand though that in the end you get some combination of symmetric polynomials with like
with some vectors of degrees
with some t's in them?
Yeah, definitely. Yes, so to say, this polynomial is not going to change itself. Just the degrees of t which appear at certain places, they're going to change themselves.
Okay.
It's like polarization, but done maybe in a strange way.
Okay, well,
Like the determinant, I suppose determinant is the easiest of all of them. So you take the determinant of your matrix, but then you change the t degrees of the elements in the matrix.
Okay, I might ask another question at the end, but I'll.
Okay, well, I don't know how far we're going to get in this talk. But, all right, so there's a certain map which does really help us to understand the connection, but with a polynomial which appear in these formulas, like here delta k minus 2, delta k minus 4, and so on. So this map is also a bit technical. So first, we start with the GLN. I take k copies of GLN and then the product with each other, and I defined a map, M with the index R, which goes to the tensor product of k minus r plus 1 copies of GLN. So we take the first r elements and just multiply them as matrices. So this is a matrix multiplication. Or you take composition of endomorphisms if you think about your matrices as endomorphisms of c to the power large N. So this is a matrix multiplication. So this is again an element of a GLN, an endomorphism. And other elements, it doesn't change. They're not involved. No, okay, no, it looks strange. It's just a map. You multiply your matrices or take composition of endomorphism. Okay, so for GLN, it's not of much use, but you can take the adjoint action of G. G is reductive finite dimensional Lie algebra. The adjoint action gives you a map from G to the GL of G. And then I apply this construction to the adjoint representation. So I multiply matrices in the adjoint representation. So again, we are going to get here something from GL of G, some endomorphism of G. And then return the product of other elements of k minus r elements which are not involved here, we didn't get into the product. Right, now the feature of Lie algebras, if you take a product of odd number of elements and then just take a product in the reverse sequence with a reverse sequence of factors, then the sum of these two terms is an element of S or G. It preserves the Killing form. So G is semi-simple, I suppose, it was prestige. And then S of G is isomorphic to the second exterior power of G. There's a certain feature of it. We're not going to end here in the GL of G. We're going to end in the SO of G. Not if you take an odd number of with elements, the product of odd number of elements. Okay, so this was for tensor powers. We can actually do it also for symmetric algebra. So first, using the symmetrization map, we send the symmetric algebra to the tensor power of G. Then we use this multiplication of matrices in the adjoint representation. And in this way, I'm going to obtain a map M with the index 2r plus 1 from the k symmetric power of G to the second exterior power of G. This stands for S of G. Now, because you have here an odd number of factors and then also you symmetrize, so you change the sequence of factors, and then also there is going to appear a product where the sequence of factors is reversed, so the sum is going to be in the S of G, and the rest remains in the symmetric algebra. So it's kind of a map which goes from the k symmetric power to the second exterior power multiplied with symmetric power k minus 2r minus 1. Now, right, it's really strange, but I'm going to use it mostly in case r is equal to 3, and it's a bit easier. So what we are doing, we are just taking products of 3 elements, and we are taking six such products because you have 6 permutations of elements 1, 2, 3. And the sum is actually an element of S of G. And if K is smaller or equal to 2, smaller than or equal to 2, when I put M from S, K is equal to 0. So M is my map, MR, the R is equal to 3. Now, it's kind of a strange map. So you'll take the first of 3 factors and take products of them in all possible sequences. Okay, so I have defined the strange maps M. M is M3 and M2R plus 1 for any R. And if G is simple, then you have a unique copy of G inside of S of G. And there are some other summands. If G is not of type A, it's actually just one of them. So if you write S of G as a sum of irreducible subrepresentations, write as 2 of them. If it is of type A, then you're going to have 3 summands. So for certain elements of a certain symmetric invariance of degree K, the images under M are going to be in the product of G with the symmetric K minus 3 power of G. So it may happen. You consider a copy of G sitting inside of S of G. I know that my M, the image of my M map M sits here. S of G turns a product with this object, and inside it there is G. So actually, I'm interested in such invariance that the image lies here, and I want even more. I want the image to be again a symmetric invariant. So everything is G equivariant. So the result is going to be an invariant of G, of a group G, but I want it to be a symmetric invariant. And this is not obvious somehow. So sometimes it's true, sometimes it's not true. I'm just looking for the invariants that have this property. Okay, I suppose. Okay, so it's always true in degree 3 because you don't have any G invariance in the second exterior power of G. All right, I think I'm running out of time, so we'll just discuss what we can discuss. So if you go back to type E, where the formulas are known because of Molev and Chervov-Talalayev, so the formulas are known, but we can actually rewrite them using this map M. And this map M actually gives you a connection between delta K and delta K minus 2R. This is just an image of delta K. This is for SLN, so I have a twiddle here above. With some combinatorially, oh, what just die. I wanted to highlight the coefficient. So with some combinatorially defined coefficient. So now, starting from type A and even still staying in type A, I can write a formula where you don't see deltas any longer. You just have a symmetric invariance H. And here, instead of other deltas, we have this strange map M, 2R plus 1 applied to the same symmetric invariant H. So this is a reformulation. It's not new, but this map M is definitely new. Right, so this formula is true in type A. It's written here for SLN. And actually, the result is that this formula is true in any type if the invariant H has this property. But the image of H under all maps M2R plus 1 is still a symmetric invariant of G. Now, if you're still in the symmetric algebra of G, after applying as many maps M as possible, then you can write the formula for the Sigel-Sugawara vector, which appeared first in type A. You can write it in any type and for any invariant, but providing it has this property. Okay, so of course, next question. If you are just interested in the symmetrization map, you just symmetrize in invariant shifted to the degree -1, and you want to know whether it is an element of a Feigin-Frenkel center. So the answer is, it is if and only if M, the image of F under the map M is 0. Okay, so it's another result. And a natural question is, of course, do such invariants H exist or not outside of type A? So far we just had examples of deltas, coefficients of a characteristic polynomial. And fortunately, yes, so such invariants do exist in other types. So for example, the Pfaffian is a very nice invariant in this aspect because M of a Pfaffian is just 0. So if you want an explicit formula for a Pfaffian type Siegel-Sugawara vector, just can obtain it by symmetrizing. And another result is that actually such invariants do exist in all classical types. So for symplectic and orthogonal Lie algebra, for the symplectic Lie algebra, we just take the coefficients of a characteristic polynomial, so they still stay in by deltas, so to say, but delta have to be of even degree to have a non-zero restriction on the sp2n. But for the orthogonal, you have to do something else. You have to take the determinant of identity matrix minus Q multiplied with your matrix. So like you take the inverse of the determinant of the inverse matrix. So not really permanence. So there are some other symmetric invariants so defined by this formula. But they have a common feature if we apply the map M to deltas in type C, or we apply the maps M to these coefficients phi to k. We're still obtaining deltas 2k minus 2r or deltas 2k minus 2r in all types. So to say for classical Lie algebras, one can write explicitly Siegel-Sugawara vectors. So this distinguished part of generators of Feigin-Frenkel center using the symmetrization map. And so using this invariance I have described above. Coefficients of a characteristic polynomial, so type C is actually very close to type A. And the orthogonal algebra, it's a bit different, so you have to take different symmetric invariants. But basically it works. All right, so the result is not, let's say, the formulas are new, but they are not first formulas that appeared for the elements of the Feigin-Frenkel center, even for types B, C, and D. So Molev had formulas, helped in formulas in 2013 using symmetrizers in the Brouwer algebra. So his initial formulas were much more complicated than what you can see here. But then in August last year, he has actually simplified his formulas after he has seen mine, and he showed that the elements coincide. So there are really some nice elements in the Feigin-Frenkel center for which you can obtain explicit formulas. So formulas are different, right? Look different, but the elements are the same. And there is a lot of information about his elements already in the literature in his book. So I just, okay, so next question, can we say something about the exceptional types? Well, yes, we can say something. So we can say that in degree 6, such nice invariants always exist, and this covers type G2, because in G2 you have just two invariants of degree 2 and degree 6, and in degree 2 this is a Casimir element, and in degree 6, here is a formula, a very explicit formula with explicit coefficients for a Siegel-Sugawara vector of degree 6, and it was obtained by hand. So no computer used. And there is also a nice feature in type E6, there is an invariant of degree 5, generating invariant of degree 5. And M of this invariant is 0. So we can just symmetrize it and obtain generator of Feigin-Frenkel center. So some partial results are available, but not complete yet. So maybe was the question how these elements look like, so what really happens to them. So now I explain what is a polarization. So basically you just change the degrees in T. So the elements Y were elements from the Lie algebra G, and you have a vector of degrees, A1 until AK, and using the symmetric group, we just change the degrees. And this is a polarization. So you take all possible permutations of your degrees and you multiply the elements by 1 until IK with degrees and add it. And you can divide by, you can divide by it, or you don't need to divide. Okay, and this is in the symmetric algebra, so it's easy to symmetrize in the symmetric algebra, but this can be also used in the enveloping algebra. Right? Don't think I have defined it here. What is this f of? Okay, so this is just a polarization of some polynomial f with respect to vectors of degree a, and it's obtained by the same formula as above. And then to get an element from the enveloping algebra, we just add here, apply the symmetrization map. Okay, so the elements of the Feigin-Frenkel center that we have obtained in this talk were actually offers from the polarizations of symmetric invariants corresponding to certain degrees, to certain vectors of degrees, and then for each degree you are going to get a combinatorial coefficient, which I cannot compute explicitly, but it's going to be some rational number. So a polynomial doesn't change it. You have some polynomial you have started with h. When you apply this map m, r times to h, obtain a certain polynomial hr, and then you change the degrees of t which appear here, and add over all possible available degrees vectors such that the total degree in t is the same as here. So let's say minus d, with certain combinatorial coefficients. Well, another, it's a bit of an application of all these things if you know that the generators of a Feigin-Frenkel center are obtained by the symmetrization. Then you can also say that the quantization of a Mishenko-Fomenko subalgebra is obtained by symmetrization, but you have to choose the generators carefully. So not for any set of generators this is going to be true. But if you take coefficients of a characteristic polynomial in types A and C, and this polynomial is phi 2k for the orthogonal algebra and Pfeffer, then it works. So there is a quantization of a Mishenko-Fomenko subalgebra given by symmetrization, and it's actually the same quantization as given by the construction of Rybnikov and Feigin-Frenkel, Toledano-Laredo, because the quantization is basically unique. It's unique on the open subset of parameters, and then both constructions are smooth in respect to parameters. So the first proof for all classical algebras was given by Molev and myself, but now we have a different proof, I would say a bit more conceptual of this fact. Okay, so a few words to conclude the talk. So I suppose for better understanding of this map M, which I have introduced today, would lead to a better understanding of some features of a Feigin-Frenkel center. For exceptional types, it's still not known whether such nice invariants exist, so that all iterated applications of the map M still remain in the symmetric algebra. It's quite probable that one can handle type F4 on a computer, E6 possibly, but I don't know. E6 is definitely much larger. As I've told you in the beginning, symmetrization is not a homomorphism of algebras, but it's a homomorphism of G models and even of current algebra models. And symmetrization behaves well with respect to taking various limits, which have been applied already. And maybe the final remark, Mishenko-Fomenko subalgebras, regular or singular, also have remarkable properties, and I think that some of these remarkable properties are still undiscovered. Right, so thank you very much for listening to my talk. This is all I wanted to present today.